Okay, this question relates to the exponential function Euler's number E, and we're going to need our calculator for this. At particular times, in T minutes, measurements are made of the temperature in degrees C of a cooling liquid, and the following results are given as temperature and time in minutes. Prove that the quantities follow a law of the form theta is equal to theta 0 times e to the power of kt, where theta 0 and k are constants, and find the approximate value of k and theta 0. So I've written the equation out here, and the first thing we're going to do, or the first thing we really should try and do, is get rid of this e. And the way you do that is you use the natural log. So I'm going to take natural logs of both sides. That's going to be the very first thing I do. The natural log theta is equal to the natural log in brackets theta 0 and k. There shouldn't be an e there because I'm trying to get rid of the e. Kt, like this. Now, whenever you have a log multiplying two values, you can actually split that up, so we end up with the natural log of theta is equal to the natural log of theta 0 plus kt, because the e disappears. The natural log is the inverse of the e, like that. The next step is to find the gradient k. Now, with k, one of the things we have to be aware of is if I've got a graph here, because this is a logarithmic function, the time element will be linear, like so. But the temperature element, which is going up here, will be logarithmic. Logarithmic, like that. We know that to find any gradient, we take the change in y and we divide it by the change in x. So I'm going to take two of the temperatures, these two here, the ones that are close together, and we have 92.9 minus, I'll leave a little gap here, 55.9, and that is divided by 10 minus 20, the change in x, 10 minus 20, like so. But because the temperatures are logarithmic, we're going to use the natural log of 92.9 and the natural log of 55.9. So I'll go into my calculator. Hope you can see this, because I can't, it's pretty dark here. So we're going to take the natural log of 92.9 is equal to 4.53. I'll take this very approximately, just for speed, minus the natural log of 55.9 is equal to 4.02, and all of that there is divided by 10, minus 10 that is, because 10 minus 20 is minus 10. So I'll do that on my calculator very quickly, and we have 4.53 minus 4.02 is equal to 0.51, and that's divided by minus 10 is equal to minus 0.051. Minus 0.051. That is K. That gives us K. And in reality, the only tricky bit is getting your head around the fact that the time is linear and the y function, the temperature, is logarithmic. Okay, so what we could do now is we can plug k back into our original equation in many different ways. So what I'm going to do is, to demonstrate this, I'm going to take a temperature. Let's have a look. I'm going to look at 55.9. So that's the temperature I'm going to use. And what we're trying to find now is this value here. Now, I just need to explain, this value is the intercept on the vertical axis. Okay, because effectively this graph follows the law y is equal to mx plus c. And because it's logarithmic, when you plot it on log paper, you'll see it's a straight line. And this theta 0 is the intercept, vertical intercept here. So I'm going to take this temperature here, okay, that one there. So I've got 55.9 is equal to theta 0, okay, times e to the minus 0.051 times 20. So I'm just going to work that power out very quickly. So the power is minus 0.102. That power. So we're going to take the E with its power over to the other side. So we have 55.9 divided by E to the minus 1.02 is equal to theta 0, like so. So we'll just find E to the minus 102 is equal to 0.3605. So we take 55.9 and we divide that. Hopefully you can see this still, because this is quite awkward. 0.3605, and that should give us this intercept here. I'll just try that out now. And roughly that's about 155 degrees C.